All right. Hi everybody. So I'm actually redoing 27 here. I did 27. Problem 27. This is chapter 7. Chapter 7. Problem 27. And I'm redoing this because I realized that I was wrong last year that I did this. And yeah, I was flat out incorrect. And so yeah, I ended up getting lucky. I ended up getting lucky last year, and so I'm really excited now to share with you kind of how to do this problem, and I'm going to do it in two ways. So all right. So here we go. How to do this? So let's see. The first way is what I'm going to consider to be the easier way. And that's this way that we're doing right here. I know, look at all this. It's the easier way. It says calculate the work done by an 85 kilogram man who pushes a crate 4 meters up along a ramp that makes an angle of 20 degrees with the horizontal, see below. So there you go. So this angle here is 20 degrees. And then he exerts a force of 500 newtons on the crate parallel to the ramp and moves at a constant speed. Be certain to include the work he does on the crate and on his body to get the ramp up. So that's kind of the hint right here as well, that we want to have the work he does on the crate and on his body to get up the ramp, right? Because the thing is that I want to emphasize here, this is a challenging problem, and mostly you guys are going to they're going to be asking you questions about like what's the work done on the crate. So we're kind of ignoring over here. But what I just thought was interesting about this problem is kind of more of a realistic situation. To get something up a ramp, you not only need to have work done on the box to get the box up the ramp, but you need to exert work to get your own body up the ramp as well. There's a lot of subtlety here, and I'm simplifying things, and I don't want to act like this isn't complicated, but I am simplifying things a little bit here. But anyway, okay. So the thing is one way to do this, and well, when I originally tried to solve this last year, and I want to thank Jaden and Fook who were with me during office hours while I was going through my little meltdown of trying to figure this out, because this is actually really good. So I was basically saying, well, all right, let's take the whole thing as being my system. If the whole thing is my system, I said, all right. So let's see, we got weight from the man, and we've also got, so that'd be like M1. I'm calling the man object 1, the box is object 2. There'd be weight from the man, M1G, and then there'd be weight from the box as well, M2G. And so both of these would be doing work. Both of these would be doing work. And that's an issue because I could do this if I knew the mass of this box. If I could do that, I could do it this way and I'd be able to figure it out and be no problem whatsoever. But because I don't know what the weight of that box is, this is where the issue came in. So I don't know, because I know that this force would be doing work, this would be doing work, and this would be doing work all on the system. But I wouldn't be able to figure that out, and that's where I hit my little snag and was like, something's wrong here. So here's like my quick way in order to do this. So the total work done by the man basically has to do work to push the box up the ramp, and the man has to do work to push himself up. So the way to do this is to separate them and do them both differently. So we got work to get the box up plus the work done to get the man up. Right? So there's work, So work, or we'll say work to get the body up, right? To get your body up. And that'd be the total work done by the man. The total work done by the man. So I'm just going to say work by the man. So total work done by the man is the work on the box and the work to get his body up there. Okay. So in order to do this, you can treat it separately. You kind of go like, all right, I'm going to ignore the man, just deal with the, and I'm not ignoring, I'm just saying like, let's say this box, what would be the total work required to get this box all the way up to the top and move at constant speed? Well, it would be, so we're treating these separately. So, this is going to be Fn2, this is going to be Fn1. So here is the box, here's to get the box up the ramp. And then there's also an applied force from the man here, right? There's an applied force from the man here. So with this situation here for the box, for the work on the box, this is kind of the easier one to do. So the work done on the box, that's just going to be, right? Because I know the only thing, to get that, the man, this is the man's work on the box, by the way. So the man is doing is this right there. That's the force applied. That's from the man here, right? So the force that the man exerts on the box would be, well, it'd be the force applied, the magnitude of the force applied, multiplied by the displacement, multiplied by cosine of the angle between those two things. So that's going to be the work done on the box is going to be, well, the applied force is 500 newtons. They told us that. And that's that. Or sorry, I won't say applied force. We'll say F, right? Because F was the F was what they said the force was. So even though it could be an applied force, we'll just say F. So we'll say F right there because that's what they said it is. So 500 newtons. Okay. So this is going to be 500 multiplied by the displacement. The displacement is 4 meters. And then cosine of the angle between those two things. So the displacement is pointing to the right and the force vector is pointing to the right. So that means then that the angle is going to be 0. So cosine of 0 is 1. So 500 times 4, the work on the box is going to be then 2,000 joules. So I got that. That's 2,000 joules right there. All right. Now what I'm going to do is ignore the box completely. So now I'm treating it as if the man, and only the man, so I'm not worried about this, so only the man is walking up the ramp. Now notice a couple things. First thing, I'm saying that the friction force between the box and the ramp is negligible. I don't need to worry about it. That's an assumption I'm making, and that's something that's kind of an issue here. However, for the man to get up the ramp, they're going to have to use the friction force, right? They're going to have to use the friction force. So now I'm ignoring this and dealing with just this. So this is the same free body diagram basically, but now we're talking about getting the man up the ramp. And obviously there's going to have to be a friction force because he's got to climb up there somehow, right? So we'll say that there's a friction force pointing like that. And So yeah, and so in order to get so there's that right there. So now in order to get the body up, the work done to get the body up. So with this, let's see. I don't know what this, I guess I could calculate this friction force and do it that way. But what I'm going to do is I'm actually going to use the work energy theorem here. So to get the man up, what would be the work required? In order to get the man up, so the net work in order to get the man up, or wait. So in order to get and here's where I must admit I'm cheating a little bit, okay? But so yeah, if you really understand physics, you'll notice I'm cheating a little bit here. Okay, but anyway, so we're basically going to say. There's going to be, there's two forces here it's doing work. The normal force is not going to do work because it's pointing perpendicular, and I guess I could make that a little more perpendicular. So it's pointing perpendicular to the displacement, right? The normal force is pointing perpendicular to displacement. That's not going to do work. But this is going to do work, and this is going to do work, and it needs to do enough work to get the man up, right? So, okay. And what I'm going to do here is I'm going to use the work energy theorem to get the man up. Remember, I'm ignoring the box and just treating this separately as just the man on his own. So the net work then, so here we go, the net work is going to equal the change in kinetic energy. And the change in kinetic energy, remember, they're saying it's moving up at constant speed. So if it's moving up at constant speed, there is no change in kinetic energy. The kinetic energy is the same throughout. So the change in kinetic energy is going to be 0. And then what's the net work? Well, there's two forces doing work here. There's the force from the man's weight, and then there's also this force of friction doing work. And so work from friction plus work from the weight from gravity. So basically, this is the Earth doing work on the man, and this is the ramp doing work on the man, or the ground, right? The ramp doing work on the man. And yeah, okay. So and that would be the well, yeah, okay. Let's and this friction force, right, is basically this is what the work that would need to be done to get the man up, right? It would be this force that's going to get the man up, and so that would be then the work that the man would have to exert on his body in order to get him up the ramp. Those of you, you know, we were just talking about energy in this class, but those of you who know energy, right, that's the energy that the man needs to put into all this in order to get himself up the ramp. That's kind of the idea behind this. Okay, so so how would we do this? Well, okay, let's see. So the work done by friction, so that's basically what I'm trying to look for. And remember, this work done by friction is going to be the work done by the body. So if I can solve for the work done by friction, I got this thing. So that's going to be, well, the work done by the Earth, by gravity. So that's going to be plus, and then work, and any kind of work is the force, the magnitude of the force, times the magnitude of the displacement, times cosine of my angle. So this is going to be mg, right? mg times the displacement times cosine of, what's the angle now between here? So we want to be careful here. So here I'm saying is the force of friction. So here's the force of friction. Let's see. So if I did, how would be the best way to do this? Oh, here we go. I could do this, right? So this is 90 degrees because I'm trying to find this angle. So the angle I'm trying to find out is this right there. So if I do this, right, that's 90 degrees right there. And then I can use similar triangles. See how this angle is the same as this angle right here? So that means this angle right here is got to be 20 degrees. So that angle has to be 20 degrees there. So I got 90 degrees right here plus 20 degrees. So the total angle then, there, I'm going to call that theta. So theta then is going to equal 90 plus 20. So it's going to be 110 degrees. So this is going to be cosine of 110 degrees, like that, equals 0. Lastly, going to isolate work of friction, because so it's going to be negative mg, because I'm subtracting all this term from both sides, delta x times cosine of 110. So if I do this, let's plug everything in now. Work done by friction is going to be mg, so that's mg. The mass of the man is 85 kilograms, so let's just plug all that in. 85 times g is 10. Displacement is 4 meters? Yeah, 4 meters. And then cosine of 110. So this is going to be 85 times 10 times 4 times cosine of 110. And I get, so all of this is negative 1,160. So all of that is negative 1,160. But there's the negative in front of here as well. So that negative is going to cancel out and leave me with the work due to friction is 1,160 joules. So remember, this work due to friction, that would be the work required to get the man, and this is the man just by himself, up the ramp. That would be the work required. And that would be the work then the man would have to exert on his body to get himself up the ramp at constant speed. So then to get finally using this last equation right here, I'll just copy it. Copy it right here, paste it at the bottom. So that is just going to be, so the work from, the total work from the man, that's the work due to the box, to get the box up, right, is 2,000 joules. Plus the work to get his body up is 1,160 joules. And so the total work by the man is 3,160 joules. So that would be the total work done by the man. And that's one way you could do it. In my previous video, I made the mistake of using both of these as my system, and then I got lucky and I made a mistake. So that's one way you could do it, though. Just treat them separately. How much would it take how much work would it take to get the box up the ramp? How much work would it take to get the man up the ramp? And there you go. Notice, those of you who know energy, it's much easier to find out how much work it takes to get the man up the ramp if you know how to use things like gravitational potential energy. But we don't know that yet, so that's why I'm not using it. All right, second way, and this is what I think is the most fun way, or at least interesting way, because this is this now using this. So I'm doing this again. Here now I'm just going to say this now, the man is my object. The man is my system. So as the man pushes everything up, what forces are acting on the man? So that's what I'm going to do here. So there we go. There's my ramp. So I'm sorry, I got really picky here. Just because I don't know how complex this is going to get. So let's see. So I'm going to make now the dot. There you go. There's the man. What forces are acting on the man? Well, there's his weight. So that's M1, right? Because that's the mass of that's what I said. The man is going to be object 1. The box is object 2. So there's M1G acting there. There's the normal force perpendicular to the surface. That's what's nice about with work. You don't really have to care much about the normal force because it's almost always perpendicular to the displacement. But then now there's, let's see. So forces acting here. There's the force. So let's see. As the man pushes up, there's that friction force again. There's that friction force again. So this is the force of friction. To get the man up. But now there's also going to be, right, as he's pushing up, he's going to feel the box pushing against him back this way. That's Newton's third law, right? He's exerting a force. He's exerting a force on the box this way, but Newton's third law says, well, yeah, but now the box is going to be exerting a force that way. So here's the force from the box going in the opposite direction there. So here we go. There's a force from the box pointing in the opposite direction there. Okay, and so I think that's it. I think that's all the forces. Yeah. All right. So we know that, we'll say it's force of the box, but it's F, right? Because it's F. It's the same force. It's just pointing in the opposite direction. It's a third law pair right there. So here's F pointing that way, and F again is 500 newtons. So the displacement again is 4 meters, and F is 500 newtons. So all right, now let's I'm going to again use work equals, so net work, this is the work energy theorem. The net work is equal to the change in kinetic energy. So the net work is equal to the change in kinetic energy. And what forces are going to be doing work? Well, this force is going to do work. The weight, so this is the earth doing work. And then the ramp is going to do work on the man as well, which would be how much work that the man needs to do in order to push himself up. Again, those of you who know energy, that's the amount of work that the man would need to exert in order to get himself up. So again, what I'm going to be trying to solve for is this force of friction, and that would be the total work done by the man to get everything up, because that'd be the work he would take to overcome his weight, and the work it would take to push the box up as well. All right, let's see what that does. So here, the net work, the total work, there's 3 works here. there's work from the friction force, and that's the work done by the man. That's the total work done by the man there. In fact, I could just replace that with the work from the man. Yeah, do I want to? Yeah, no, I'm going to keep it. I'll just keep it. But let's at least identify that. So work of friction would be the work done by man, right? Yeah, so we're going to add that then to the work done by the earth, by gravity, pulling down on the man. Remember, I don't need to care about the box's weight, though, right? Because I'm not including that in my system. But the box is still exerting a force down on the man right here. So plus the work done by the box from that force right there equals the change in kinetic energy. And remember, they said that moving up at constant speed. So if he's moving up at constant speed, then the change in kinetic energy is 0 because there's no change in speed. So, right, because kinetic energy is 1/2 mv squared, so it'd be mv final squared minus mv initial squared. So if there's no change in speed, boom, that's just going to be 0. So we don't need to worry about that. So all this is going to be equal to 0. Let's see now. The work done by the box, right, by the box, well, that's going to be the magnitude of the force itself. Multiplied by the magnitude of the displacement, multiplied by cosine of the angle between those two things. So that's going to be the work done by the frictional force is going to be that force F multiplied by the displacement. So these are just the magnitudes times cosine of the angle between the force F and the displacement. Well, this force, right, is pointing that way, down and to the left there, where, oh, this is also 20 degrees, right? And the displacement here is pointing to the right, right? So, oh, they're pointing completely opposite of each other, so the angle between them is 180 degrees. So that's going to be, well, and then cosine of 180 is -1. Let's just do that. So cosine of 180 is -1, so the work done by friction is negative F delta X, and we'll plug in those stuff later. So I'll take all that and plug that in there. Let's actually write down work of friction plus work of gravity plus work of that force. So I got that. So now I can replace this with being the work of, oops, that's not baby F, capital F, right? Baby F is the work from friction, work from gravity, plus, and this is going to be negative F delta X right there, because the negative from the cosine 180 equals 0. All right, now let's do the work from gravity. So the work due to gravity, well, that's going to be, because again, this is what I'm, so all I'm doing is trying to solve for this. All I'm doing is trying to solve for this. So work due to gravity, well, that's going to be mg, that's the magnitude of the weight, multiplied by the displacement, multiplied by the angle between it. Right, not the magnitude, though. This is what kind of dictates your sign. So what's the angle? What's the angle between here? Well, okay, once again, I can do, oh, I'll just, I'll just make a horizontal here. This is going to be, so again, I'm trying to find this angle right here, theta. So that first part right there, that's going to be 90 degrees. That's 90 degrees because I just drew a horizontal right there. And this here, using those similar triangles ideas, this angle and this angle are going to be the same. Or it's not using similar triangles, it's using, right, two parallel. Those are parallel lines with a segment in between there. So alternate interior or something like that. So this has got to be 20 degrees as well. So then theta then is going to be 90 plus 20. You can see it's the same idea. So it's 110 degrees. So, okay, the angle here then is going to be 110 degrees. So the work done by gravity is going to be mg delta x times cosine of 110 degrees. All right, and then now I'm going to replace all that, and that's going to go in here. So this is going to be then the work done by friction plus mg delta x times cosine of 110 minus f delta x equals 0. So I got everything. I just need to isolate now this frictional force. And remember, this is what I'm trying to find. This is going to be the work that the man does, right, to pull his weight up and the box, to push the box. That's what this whole thing is doing here. So I'm going to isolate this. So it's going to be the force times the displacement. And this is going to be minus mg delta x cosine of 110. So let's plug in some numbers now. The work of friction, which is the work that the man does, is the force, which is 500 newtons, times the displacement, which is 4, minus the man's weight is 85, g is 10, displacement is 4, and then cosine of 110. So this is going to be 2,000 joules. And then this is going to be minus 85 times 40, because 10 times 4 is 40. So 85 times 40 times cosine of 110. That's going to be negative 1,160, rounding a little bit there. So negative 1,160. Negative, so if you subtract a negative, that's going to be adding together. So it's going to be 2,000 plus 1,160. And look at that. You get exactly the same answer there. So it's going to be 3,160 joules of work in order to get up there, which is the work that the total work that the man does there. So yeah, both ways work there. I just thought it was interesting. I often love that, with physics, is that you can do things two different ways and get the same answer. And I also wanted to correct and clarify my original video if you accidentally saw it. And I apologize to people last year as well. All right, so hopefully that helps. Take care. See you later. Bye.